Diamond. On Earth, it's one of the rarest and most expensive materials we've ever pulled from the ground. A symbol of value, wealth, and permanence. We spend lifetimes mining for it, polishing it, selling it, all because of how little of it exists here. But tonight, we're going somewhere very different. Around 41 light-years from Earth, there's a planet roughly twice the size of Earth and 8 times its mass, orbiting so close to its star that a full year lasts just 18 hours. This world, known as 55 Cancri E, may contain more diamond than any other known object in the universe. A super-Earth where crystallized carbon could make up a significant portion of the interior. Think about what that means for a second. A world where diamond isn't treasure, it's geology. Where what we mine like gold and guard like wealth might be as common as ordinary rock. The discovery of this world challenged our assumptions about how planets form and reminded us that the cosmos creates treasures on scales we've barely begun to understand. Around 41 light-years from Earth in the constellation Cancer, 55 Cancri E sits in a class of planets known as super-Earths. Worlds larger than our own, but smaller than Neptune. What sets this particular super-Earth apart is the possibility that its interior chemistry differs fundamentally from Earth's, dominated by carbon rather than the oxygen and silicon that form our planet's rocky foundation. Under the immense pressures found within such a massive world, carbon wouldn't just compress, it would crystallize. Diamond, the hardest natural substance known, forms when carbon atoms are compressed under extreme pressure and temperature, forcing them into a rigid crystalline lattice. On Earth, this happens about 150 kilometers below the surface, and only in rare, perfect pockets of conditions. On 55 Cancri, such conditions may exist throughout vast regions of the planetary interior. This is a world where precious gems aren't treasures at all, where the ground beneath the molten surface may glitter with crystals extending for thousands of kilometers in every direction. The concept challenges our earthbound sense of value, transforming diamond from something rare and precious into something as common as the basalt and granite that form our own planet's crust. You're watching the Drowsy Astronaut, and tonight we're traveling 41 light-years to explore a world that may contain more crystallized carbon than any place humanity has ever discovered. This journey moves slowly, meant for resting, unwinding, or keeping in the background as your mind settles. If this channel helps you find a moment of calm among the stars, a like or subscribe genuinely supports these explorations. Now, let us begin. The possibility that 55 Cancri E might be a diamond planet emerged from careful analysis of its mass and radius, the two fundamental measurements that reveal a planet's density and hint at its composition. When astronomers first determined these values, they found a world denser than expected for a planet composed of the same materials as Earth. Something about this world's interior had to be different. The density of a planet tells us what materials might be packed inside, with denser worlds containing more heavy elements or more tightly compressed materials than their lighter counterparts. 55 Cancri has a density slightly higher than Earth's, despite being larger, suggesting either an unusually large iron core or an unusual composition throughout. The carbon planet hypothesis emerged as one compelling explanation. If the planet formed from material rich in carbon rather than the oxygen-dominated material that built Earth, its entire chemistry would differ from what we know. Carbon-rich planets would contain minerals unknown in our terrestrial geology, with graphite and diamond replacing the silicate rocks that cover Earth's surface. The interior would be a realm of pure carbon in its various forms. The pressure at the center of 55 Cancri A exceeds anything found within Earth, crushing matter into configurations that our surface-dwelling experience cannot intuit. At such pressures, carbon atoms have no choice but to pack as tightly as physics allows, forming the crystal structure we call diamond. The process requires no special conditions beyond pressure and time. The carbon that might form this diamond world originated in stars that died before the 55 Cancri system was born. Nuclear furnaces that fused lighter elements into heavier ones over millions of years. Carbon is forged in the cores of stars through a process called triple alpha fusion, where 3 helium nuclei combine under extreme conditions. This carbon is then scattered into space when stars explode or shed their outer layers. The material that would eventually become 55 Cancri E drifted through space for eons before gravitational attraction drew it together into a rotating disk around a newly forming star. Within this disk, dust grains collided and stuck together, gradually building larger and larger objects over millions of years. The composition of those original grains determined what kind of planet would eventually form. In our own solar system, the protoplanetary disk contained more oxygen than carbon, leading to the formation of silicate-rich rocky planets like Earth. Around 55 Cancri, the ratio may have been different, with carbon matching or exceeding oxygen in abundance. This single chemical difference would produce worlds utterly unlike our own. A planet forming from carbon-rich material would have no quartz, no feldspar, no olivine, the common minerals that make up Earth's crust and mantle. Instead, it would contain graphite, silicon carbide, iron carbide, and under sufficient pressure, diamond. The geology would be alien from the atomic level upward. The diamond within 55 Cancri, if it exists, would not resemble the gems that humans prize for jewelry and industrial applications. There would be no individual crystals separated from surrounding rock, no clear boundaries between diamond and other materials. Instead, the diamond would form continuous masses, perhaps mixed with other carbon phases, extending through the planet's deep interior. Imagine a layer of diamond, perhaps 1,000 kilometers thick, surrounding a metallic core and underlying a mantle of graphite and other carbon minerals. The pressures that maintain this diamond are so extreme that the material has no choice but to remain in its densest configuration. Only if the planet were somehow broken apart would the pressure release enough for the diamond to transform. The color of such diamond would likely not be the clear transparency we associate with gemstones, as impurities and the sheer scale of the material would alter its optical properties. The diamond might appear yellow, brown, or even black, depending on what other elements are mixed into the carbon lattice. Beauty would exist at scales too large for any eye to perceive. The total mass of diamond within 55 Cancri E, if the carbon planet hypothesis is correct, would exceed all the diamond ever mined or imagined on Earth by factors beyond meaningful comparison. Our entire planet's diamond deposits would constitute a rounding error in the ledger of 55 Cancri's crystalline interior. The formation of such a world required conditions specific to the 55 Cancri system, a star with the right composition feeding a protoplanetary disk with elevated carbon abundance. Not every planetary system would produce carbon planets, just as not every system produces gas giants or ice worlds. The diversity of outcomes reflects the diversity of initial conditions. The star 55 Cancri A is roughly 10 billion years old, more than twice the age of our Sun, having formed when the galaxy itself was younger, and chemical abundances differed from today. Older stars sometimes show unusual element ratios, the legacy of the specific supernovae and stellar winds that contributed material to their birth clouds. This age may explain the unusual composition. Carbon planets are thought to be relatively rare, requiring the right stellar chemistry to produce the necessary conditions in the protoplanetary disk. Most stars have carbon-to-oxygen ratios similar to our Sun, which favors the formation of silicate planets like Earth. But around stars, where carbon is enhanced, diamond worlds become possible. 55 Cancri may represent one of the best examples of a carbon planet that we can study with current technology, close enough that detailed observations are possible, extreme enough that its unusual nature can be detected. The planet serves as a natural laboratory for testing theories about how carbon worlds behave. The concept of a diamond planet captures imagination in ways that other astronomical discoveries do not, tapping into human associations with value, beauty, and rarity. Yet the true wonder lies not in the economic implications, no one will ever mine this world, but in the sheer creativity of natural processes. The universe builds with whatever materials are available. On Earth, carbon is the element of life, forming the backbone of every organic molecule in every living thing that has ever existed on our planet. On 55 Cancri, that same element may form the backbone of geology itself, crystallized into vast structures that would endure for billions of years. The element is the same, but the outcome could not be more different. The diamond planet reminds us that the cosmos does not share our sense of proportion or value, that it creates wonders carelessly, without intention, following only the laws of physics wherever they lead. What we consider precious, the universe scatters with abandon in the right conditions. What we consider ordinary, the universe may never produce at all. 41 light-years away, this crystalline world continues its 18-hour orbit, racing around its parent star while potentially containing more diamond than all the stars visible in Earth's night sky have ever produced. The treasure exists whether or not anyone values it, whether or not anyone ever beholds it. Whatever diamond may lie beneath the surface of 55 Cancri, the surface itself presents a vision far removed from any gemstone's sparkle, a hellscape of molten rock and extreme temperatures that would destroy any probe humanity could currently build. The day side of this planet, perpetually facing its nearby star, reaches temperatures around 2,000 degrees Celsius, hot enough to melt most metals and vaporize many common materials. The planet orbits its star at a distance of roughly 2.4 million kilometers, less than 2% of the distance between Earth and our Sun. So close that the star would appear enormous in the sky, if any sky exists to see it through. At this proximity, the gravitational grip of the star has locked the planet's rotation, ensuring that the same hemisphere always faces the stellar furnace. The day side burns while the night side faces the cold of space. This tidal locking creates a world of extremes, with temperature differences between the two hemispheres that may exceed 1,000 degrees Celsius. The day side is a realm of perpetual noon, with the star fixed at a position in the sky that never changes, pouring radiation onto rocks that have been molten for billions of years. The night side knows no dawn, only endless darkness. Observations of 55 Cancri have detected what appears to be variability in the heat radiating from the planet. Brightness changes that suggest the surface conditions shift over time rather than remaining static. This variability points to dynamic processes, perhaps volcanic activity, perhaps flowing lava redistributing heat across the surface. The planet is not merely hot, but actively churning. The surface of the dayside may be covered by a global ocean of liquid rock, magma flowing across a landscape that has no solid crust to contain it. On Earth, lava cools and solidifies when it reaches the surface, building new rock and eventually forming the stable ground we walk upon. On 55 Cancri A, the constant stellar heating prevents solidification, keeping the surface permanently molten. This lava ocean would glow with the light of its own heat, radiating in orange and red wavelengths that blend with the light from the nearby star to create illumination unlike anything on Earth. The distinction between ground and sky might blur, with the glowing surface and the radiant star merging into a continuous field of light and heat. Darkness would exist only on the far side. The composition of this lava ocean depends on what minerals exist in the planet's outer layers, and for a carbon-rich world, the chemistry would differ substantially from the basalt and granite that dominate Earth's volcanism. The molten material might include exotic compounds of carbon, silicon, and various metals, flowing in ways that our terrestrial experience cannot predict. Volcanic features on such a world would be built from unfamiliar materials, perhaps graphite instead of basalt, perhaps carbide compounds instead of silicate glasses. The structures that form when this alien lava cools, if it ever cools on the day side, would constitute geology textbooks not yet written. The night side of 55 Cancri A presents a different extreme, a hemisphere that receives no direct starlight and must radiate its heat into the cold of space with nothing to replenish it. Temperatures on the night side are cooler than the day side, though perhaps not cold by Earth standards, with heat transported around the planet by atmospheric or surface flows. If an atmosphere exists, winds would blow from the hot day side toward the cooler night side, carrying thermal energy and perhaps vaporized rock material around the planet. These winds might reach tremendous speeds, driven by the temperature gradient between the two hemispheres. The atmosphere itself would be exotic, containing whatever gases can exist at such extreme temperatures. The boundary between day and night, the terminator zone, would be a region of transition where conditions shift from infernal heat to relative coolness over a relatively short distance. Here, lava from the day side might begin to solidify as stellar heating diminishes, perhaps creating a ring of volcanic activity where molten and solid phases meet. Any solid surface that exists on 55 Cancri likely exists only in this transition zone or on the night side, where temperatures drop enough to allow rock to crystallize. The day side may have no solid ground at all, only the churning surface of a magma ocean deeper than any body of water on Earth. The visual experience of this world, imagined from some impossible vantage point, would overwhelm human senses evolved for the gentle environment of Earth, with brightness and heat beyond anything our experience prepares us to imagine. The nearby star would dominate the dayside sky, perhaps spanning many degrees of arc, blazing with an intensity that would instantly blind unprotected eyes. The color of light on the day side would be shifted compared to Earth's sunlight, with the specific spectrum depending on the properties of 55 Cancri and any filtering by the planet's atmosphere. The star is slightly cooler than our sun, which might give the light a slightly warmer, more orange tint than we experience on Earth. Below this blazing sky, the surface would glow with its own light, magma radiating heat in visible wavelengths that add to the illumination from above. The ground would not be dark but luminous, contributing its own orange and red light to the infernal scene. Shadows might barely exist when the surface itself is a light source. The sound of such a world, if sound could propagate through whatever atmosphere exists, might include the constant roar of flowing lava, the hiss of vaporizing rock, perhaps the rumble of volcanic explosions releasing pressure from below. The stillness we associate with space would be absent, replaced by geological violence on a scale we cannot match on Earth. The density of 55 Cancri, combined with its size, creates surface gravity roughly twice Earth's, meaning any hypothetical object on its surface would weigh twice what it weighs at home. This increased gravity helps contain any atmosphere the planet possesses against the stripping effects of the nearby star's radiation and stellar wind. The combination of extreme heat and elevated gravity creates conditions where rock itself behaves differently than it does on Earth, with viscosity and flow rates altered by the specific temperature and pressure conditions. The lava ocean would have its own fluid dynamics, currents and eddies driven by convection as heat rises from below. Beneath the molten surface, conditions grow even more extreme as depth increases, with pressures climbing rapidly under the weight of the overlying material. Somewhere below, perhaps a few hundred kilometers down, conditions may become suitable for carbon to crystallize into diamond, creating the transition from surface inferno to interior gemstone. The contrast between surface and interior could not be more stark. Liquid fire above, crystalline diamond below, connected by continuous rock whose phase changes with depth. The planet is both furnace and vault, both chaos and perfect order, depending only on how deep you consider. Observations of 55 Cancri have revealed that its brightness varies over timescales of days to weeks, changes that suggest real physical alterations on or above the surface rather than mere instrumental noise. The leading interpretation is volcanic activity, eruptions that change the reflectivity or emissivity of the surface as lava flows and cools. This variability makes 55 Cancri one of the most geologically active worlds we have ever observed beyond our solar system. A planet where the surface never settles into equilibrium, but constantly remakes itself. The same internal heat that may maintain diamond in the interior drives convection that reaches the surface as volcanism. The scale of this volcanic activity would dwarf anything on Earth, where our largest eruptions produce lava flows measured in cubic kilometers over periods of years. On 55 Cancri, the entire dayside surface may participate in continuous volcanic cycling, with volumes of lava that would cover continents flowing across the planetary face. This activity has likely continued for billions of years, since the planet settled into its present orbit and tidal locking established the permanent day-night division that drives the thermal extremes. The volcanism is not occasional but constant, not localized but global, a fundamental feature of how this world operates. Despite the hellish surface conditions, 55 Cancri represents one of the most studied exoplanets outside our solar system, a target of observations from both ground-based and space-based telescopes seeking to understand its atmosphere, composition, and variability. The planet's proximity to its star makes it bright enough to detect during secondary eclipse when it passes behind the star, and its own thermal emission temporarily vanishes. These observations have revealed that the planet is dark, absorbing most of the light that falls upon it, rather than reflecting it back into space as a more reflective world would. The dark surface is consistent with graphite or other carbon materials, which absorb light efficiently, though it could also result from other dark minerals. The temperature measurements from these observations confirm the extreme heat of the day side, while suggesting that some heat transport occurs toward the night side, evening out temperatures slightly from what pure radiation would predict. Either atmospheric winds or subsurface lava flows must carry energy around the planet. Future observations with more powerful telescopes may reveal additional details about this world, perhaps constraining its atmospheric composition, perhaps mapping temperature variations across its surface with higher precision. Each new observation adds to our understanding of how extreme worlds function. The star that hosts this diamond world shines in the northern constellation Cancer, a point of light visible to the naked eye under dark conditions, one of the relatively few planet-hosting stars that humans can see without optical assistance. 55 Cancri is a G-type star, the same stellar category as our Sun, though with significant differences in size, temperature, and age that make its planetary system unique. This star is approximately 96% the mass of our Sun and about 94% its diameter, making it slightly smaller and cooler than the stellar companion that has warmed Earth for 4.5 billion years. The surface temperature of 55 Cancri is roughly 500 degrees Celsius cooler than the Sun, giving its light a slightly warmer, more orange tint. The age of this star sets it apart from our Sun most dramatically, with estimates placing it at roughly 10 billion years old, more than twice the age of our solar system. This venerable star has burned steadily for longer than the Sun has existed, witnessing the formation and evolution of its planetary system across timescales that humble our human perspective. At this age, the star has used a significant fraction of the hydrogen fuel in its core, slowly evolving toward the latest stages of stellar life that still lie billions of years in the future. The star will eventually expand into a red giant, potentially engulfing its innermost planet, but this fate remains distant on any timescale that matters to present observers. 55 Cancri is actually a binary star system, with the bright G-type primary accompanied by a faint red dwarf companion designated 55 Cancri b. This companion orbits at a tremendous distance, roughly 1,000 astronomical units from the primary, taking many thousands of years to complete a single orbit around their common center of mass. At such a vast separation, the red dwarf companion has minimal gravitational influence on the inner planetary system, where 55 Cancri resides, too distant to perturb planetary orbits or disrupt the delicate arrangements that have persisted for billions of years. The companion is more a distant observer than an active participant in the system's dynamics. The red dwarf itself is a small, cool star, perhaps 1/3 the mass of the Sun, and far dimmer than its larger partner. From the surface of 55 Cancri, if surface observation were possible, this distant companion would appear as merely a bright point of light in the sky, distinguishable from background stars, but far too distant to provide meaningful warmth or illumination. Binary star systems are common in the galaxy, with roughly half of all Sun-like stars having at least one stellar companion. The wide separation in the 55 Cancri system places it in a category where the binary nature has little practical effect on the planets. Unlike close binary systems where stellar gravity can destabilize or prevent planetary formation, the chemical composition of 55 Cancri A differs from our Sun in ways that may have influenced the formation and nature of its planets, including the potential carbon richness that makes the diamond planet hypothesis plausible. Spectroscopic analysis of the star's atmosphere reveals the abundances of various elements which reflect the composition of the material from which both star and planets formed. Early analyses suggested that 55 Cancri A has a carbon-to-oxygen ratio higher than the Sun's, potentially approaching or exceeding unity. If the ratio exceeds 1, carbon becomes more abundant than oxygen in the system, favoring the formation of carbon-rich planets rather than the silicate worlds that dominate our solar system. More recent analyses have complicated this picture, with different studies finding different carbon-to-oxygen ratios depending on methods and assumptions. The stellar composition remains somewhat uncertain, as does the direct link between stellar and planetary composition. The diamond planet hypothesis is plausible, but not confirmed by stellar observations alone. What is clear is that the star is metal-rich, containing higher abundances of elements heavier than helium than the Sun does. Metal-rich stars are more likely to host planets, particularly massive planets, because the additional heavy elements provide more raw material for planet building in the protoplanetary disk. The brightness of 55 Cancri A in Earth's sky at apparent magnitude 5.95 places it just at the edge of naked eye visibility for observers with good vision and dark skies. Light pollution easily overwhelms this faint star, but from rural areas or dark sky preserves, patient observers can locate it in the constellation Cancer between the brighter stars of Gemini and Leo. This visibility connects us directly to the diamond world in a way that most exoplanets cannot offer, allowing us to look toward the actual star whose light warms and illuminates this exotic world. The photons entering a dark adapted eye at night have traveled for 41 years from the surface of a star that hosts one of the strangest planets ever discovered. The constellation Cancer is not among the more prominent star patterns, often overlooked in favor of its brighter neighbors, but it contains within it this remarkable planetary system worthy of contemplation. Ancient observers who named the constellation knew nothing of the worlds orbiting its dim stars, seeing only points of light arranged in patterns that suggested crabs or other creatures from earthly experience. The planets remained hidden, their existence unsuspected, until instruments sensitive enough to detect their subtle influences were finally developed in recent decades. The distance to 55 Cancri, approximately 41 light-years, places it among the closest stars to our solar system, a neighbor in the vast suburban sprawl of the Milky Way galaxy. This proximity makes the system an excellent target for detailed study, close enough that our best instruments can tease out information that would be impossible to obtain from more distant systems. Light traveling from 55 Cancri to Earth departs the star and crosses the void for just over 4 decades before arriving at our telescopes and eyes. The photons we observed tonight left the star around 1983 or so, beginning their journey while the first personal computers were appearing in homes and the internet had not yet been invented. This is a short journey by cosmic standards, a mere hop across the neighborhood compared to the thousands or millions of light years that separate us from galaxies and distant stellar populations. The relative proximity of 55 Cancri has made it one of the most studied exoplanetary systems known. The proper motion of the star, its slow drift across the sky relative to more distant background stars, is measurable over years of observation, but negligible on human timescales. The constellation Cancer will maintain its familiar shape for thousands of years yet, with 55 Cancri remaining a steady point within its boundaries. The star has been known to astronomers for centuries, catalogued and measured long before anyone suspected it hosted planets, let alone a world potentially made of diamond. The name 55 Cancri simply indicates that it was the 55th star, catalogued in the constellation Cancer, according to the system established by John Flamsteed in the early 1700s. The evolution of 55 Cancri over its 10 billion-year lifetime has been slow and steady, the gradual consumption of hydrogen fuel in the core proceeding at a measured pace dictated by the star's mass. Larger stars burn through their fuel quickly and die young, while smaller stars can last for trillions of years. A G-type star of this mass will eventually exhaust the hydrogen in its core and begin fusing hydrogen in a shell around an inert helium core, causing the outer layers to expand and cool. This red giant phase lies perhaps 5 billion years in the future for 55 Cancri, a fate that will dramatically alter the inner planetary system. When the star expands, it will likely engulf or destroy 55 Cancri, the diamond planet that currently orbits so close. The distance between star and planet is small enough that even modest stellar expansion would bring the planet within the outer atmosphere of the swelling star. The diamonds would vaporize. But this destruction lies far in the future, distant enough that it need not concern us tonight as we contemplate the present state of this remarkable system. For now, the star burns steadily, the planet orbits every 18 hours, and the diamond interior remains locked beneath a molten surface. The stability of the star over billions of years has allowed its planetary system to reach a mature state, with orbits that have long since settled into their current configurations. Whatever chaos accompanied the system's formation has long since damped away, leaving the orderly arrangement of 5 known planets that astronomers observe today. This stellar stability extends to the output of light and heat, which varies only slightly over timescales that matter to planetary climates. The star is not significantly variable, meaning the diamond planet receives a relatively constant flux of radiation year after year, century after century. The spectral type of 55 Cancri, classified as G8V, indicates a star on the cooler end of the G-type range, approaching the boundary with K-type orange dwarfs. This cooler temperature affects the spectrum of light the star emits, shifting it slightly toward longer wavelengths compared to our Sun. The light-warming 55 Cancri is therefore slightly different in character from sunlight, with proportionally more orange and red wavelengths and fewer blue and ultraviolet. This difference would be subtle to human eyes, but significant for processes that depend on specific wavelengths, such as photosynthesis, if any equivalent process could exist on such a hostile world. The luminosity of the star is approximately 60% that of the Sun, meaning it produces less total light and heat despite being nearly the same size. This lower output would make the habitable zone of the system lie closer to the star than in our solar system, though 55 Cancri orbits far inside even this closer habitable zone. The star's properties have been measured with considerable precision through decades of observation using spectroscopy, photometry, and other techniques. Astronomers know its mass, radius, temperature, age, and composition better than they know most stars, thanks to the intensive study prompted by its planetary system. The concept of a carbon planet challenges our assumptions about what worlds can be made of, assumptions shaped entirely by our experience with Earth and the other rocky bodies in our solar system. Here, silicon and oxygen dominate the rocks beneath our feet, combining in countless ways to form the silicate minerals that make up our crust and mantle. On a carbon planet, this familiar geology would be replaced by something utterly different. A world built from carbon compounds where graphite and diamond take the place of granite and basalt. The very ground would be chemically alien, composed of materials we normally encounter only in pencils, jewelry, or industrial applications. The possibility of carbon planets arises from variations in the carbon-to-oxygen ratio in the clouds of gas and dust from which planetary systems form. In our solar system, oxygen is more abundant than carbon, which means most carbon atoms get locked up in carbon monoxide and carbon dioxide molecules, leaving abundant oxygen to combine with silicon and form silicate rocks. If the ratio reverses, with carbon more abundant than oxygen, the chemistry changes dramatically. Oxygen gets consumed by carbon compounds, leaving excess carbon free to dominate the solid materials that condense from the cooling nebula. Instead of silicate rocks, you get graphite, carbides, and under sufficient pressure, diamond 55 Cancri may represent our best candidate for a carbon world, a natural example of this exotic planetary type that theory predicted before observation confirmed. The combination of the planet's measured density, the possible carbon enrichment of its parent star, and theoretical models of planetary interiors all point toward a carbon-rich composition. The density of 55 Cancri, derived from its measured mass and radius, is consistent with a world containing significant carbon, but does not uniquely require it. The same density could arise from different mixtures of materials, making the determination of composition from density alone ambiguous. Theoretical models of carbon planet interiors suggest a layered structure quite different from Earth's arrangement of crust, mantle, and core. The outermost layers might be graphite, the familiar soft form of carbon that we use in pencils and lubricants, stable at lower pressures near the surface. Beneath the graphite layer, increasing pressure would force carbon atoms into the denser diamond structure, potentially creating a thick diamond mantle that extends for hundreds or thousands of kilometers toward the core. This diamond layer represents the bulk of what makes this world famous, though it lies hidden beneath the surface. The core of a carbon planet might still be iron or iron-nickel, similar to Earth's core, as iron remains an important product of stellar nucleosynthesis, regardless of the carbon-to-oxygen ratio. Alternatively, the core might contain iron carbide, a compound of iron and carbon that could form under the reducing conditions of a carbon-rich world. The surface of a carbon planet would be unlike any landscape in our solar system, dominated by carbon minerals rather than the silicates we know on Earth, Mars, and the Moon. Instead of sandy deserts or rocky mountains made of quartz and feldspar, a carbon world might feature plains of graphite and peaks of silicon carbide. Silicon carbide, known commercially as carborundum, is an extremely hard material used as an abrasive and in high-temperature electronics. On a carbon planet, it might be a common rock-forming mineral, the carbon world equivalent of the ordinary stones we walk on every day without a second thought. The color of such a world would likely be dark, as carbon minerals tend toward black and gray, rather than the browns and tans of silicate rocks. A carbon planet viewed from space might appear darker than Earth, absorbing more light and reflecting less. A dim world against the blackness of space. Of course, 55 Cancri is too hot for us to see its surface composition directly, as the molten lava covering the dayside obscures whatever carbon minerals might exist beneath. The diamond interior is inferred rather than observed, a conclusion drawn from models rather than direct detection. The formation of a carbon planet requires specific conditions in the protoplanetary disk, the cloud of gas and dust that surrounds young stars and provides the raw materials for world building. The carbon-to-oxygen ratio in this disk determines what kinds of solids can condense as the disk cools, favoring either silicates or carbon compounds. This ratio might vary across a single disk, with different regions having different compositions due to the complex chemistry of ice lines, temperature gradients, and the migration of dust and gas. A planet forming in a carbon-rich region might acquire a carbon-dominated composition, even if the overall disk averaged a lower carbon abundance. Alternatively, the entire disk might be carbon-enriched if the parent star itself formed from carbon-rich material, a rare but possible circumstance that could produce an entire system of carbon worlds. The composition of 55 Cancri has been studied intensively to determine if this explanation applies. The uncertainty in stellar composition measurements makes it difficult to determine conclusively whether the 55 Cancri system is carbon-rich enough to produce diamond planets. Different studies have yielded different results, and the question remains open despite years of investigation. What we can say with confidence is that carbon planets are theoretically possible, and that 55 Cancri matches many of the predicted characteristics of such a world. The planet is dense, it orbits a star that might be carbon-rich, and its properties are consistent with models of carbon planet interiors. The diamond that would comprise much of this world's interior differs from the diamonds we know on Earth in scale, but not in fundamental nature. Diamond is simply carbon atoms arranged in a specific crystalline structure, forced into this configuration by extreme pressure, regardless of whether that pressure exists in Earth's mantle or a super-Earth's interior. The pressures inside 55 Cancri far exceed those anywhere inside Earth, reaching levels that would compress carbon into diamond throughout vast regions of the planetary interior. A super-Earth twice the diameter and 8 times the mass of our world generates enormous pressures simply through its own gravity. Earth does contain diamonds, formed deep in the mantle where pressures are high enough to stabilize the diamond structure, then brought to the surface by volcanic eruptions that sample these deep regions. But the volume of diamond inside Earth is tiny compared to what might exist inside a carbon-rich super-Earth. If the diamond planet hypothesis is correct, 55 Cancri contains more diamond than all the diamond ever mined on Earth by a factor of billions upon billions. The comparison becomes almost meaningless at such scales, like comparing a grain of sand to a mountain range. The orbit of 55 Cancri brings it closer to its star than any planet in our solar system approaches the Sun. A proximity so extreme that the planet completes a full year in just 18 hours. While Earth takes 365 days to circle the Sun, this world races around its star twice in the time it takes us to experience a single day. The orbital distance is approximately 0.015 astronomical units, meaning the planet orbits at roughly 1/60th the distance between Earth and the Sun. Mercury, the closest planet to our Sun, orbits at about 0.4 astronomical units, making it seem distant by comparison to this extreme world. At this proximity, the gravitational grip of the star on the planet is immense, strong enough to raise tidal bulges in even the solid body of a rocky world. These tidal forces have long since locked the planet's rotation to its orbit, forcing it to keep one face permanently turned toward the star. This tidal locking means the planet rotates exactly once for each orbit, ensuring that the same hemisphere always faces the blazing stellar surface. The day side experiences eternal day, bathed in radiation that heats it to thousands of degrees, while the night side faces away into perpetual darkness. The orbital velocity of 55 Cancri E is tremendous, as the planet must move quickly to complete such a tight orbit in just 18 hours. The planet races around its star at roughly 200 kilometers per second, far faster than any planet in our solar system moves through space. Mercury, our speed champion, orbits at about 47 kilometers per second, making it seem almost leisurely compared to the diamond planet's frantic pace. The speed is necessary to balance the stronger gravity at such close range, preventing the planet from spiraling inward to its destruction. Despite this speed, the orbit is remarkably stable, having persisted for billions of years without significant decay or disruption. The planet found its current orbit early in the system's history and has maintained it ever since, racing around the star countless billions of times. The orbital period of 17 hours and 40 minutes has been measured with extreme precision through years of observation, timing the subtle dimming that occurs when the planet passes in front of its star. Each transit provides another measurement, refining our knowledge of the orbit to extraordinary accuracy. The star as seen from 55 Cancri E would appear enormous compared to our Sun as seen from Earth, spanning many degrees across the sky of the planet's dayside hemisphere. The angular size depends on both the star's physical diameter and the viewing distance, and at such close range, the star would dominate the visual field. From Earth, our Sun spans about half a degree, roughly the width of a finger held at arm's length. From 55 Cancri, the star would span perhaps 10 times that angle or more, a looming presence that covers a significant portion of the sky. The intensity of radiation at this distance is proportionally greater as well, with the inverse square law ensuring that proximity translates directly into increased flux. The planet receives thousands of times more radiation per unit area than Earth receives from the Sun. This intense radiation is what heats the dayside to temperatures exceeding 2000 degrees Celsius, hot enough to melt rock and vaporize many materials that we consider solid and stable. The energy pours down continuously, never relenting because the planet never turns away. The tidal locking that results from this extreme proximity creates a world of stark contrasts, with one hemisphere experiencing conditions radically different from the other. The day side is a realm of fire and flowing rock, while the night side is cooler, though still far warmer than any place on Earth. Heat transport from the day side to the night side occurs through atmospheric circulation and possibly through flows of molten material, evening out the temperature difference to some degree. Without any heat transport, the night side would cool toward the temperature of deep space. But the planet's atmosphere prevents such extreme cooling. The boundary between day and night, the terminator line, represents a region of transition where temperatures change rapidly across relatively short distances. This boundary circles the planet continuously, a permanent feature that has existed for billions of years. Winds likely blow from the day side toward the night side, driven by the pressure differences that result from the temperature contrast between the two hemispheres. These winds might be fierce by Earth standards, racing around the planet in patterns unlike any weather system we experience. The extreme orbit of 55 Cancri E also subjects the planet to intense tidal forces that may affect its internal structure and geological activity. The gravitational pull of the star varies across the diameter of the planet, stronger on the near side than on the far side, creating stresses that can heat the interior. This tidal heating may contribute to the volcanic activity inferred from observations, providing an additional energy source beyond the stellar radiation that heats the surface directly. The interior of the planet might be partially molten throughout, kept warm by the continuous flexing of tidal forces. The orbit is not perfectly circular, but slightly elliptical, with an eccentricity of about 0.05. This small departure from circularity means the tidal stress varies slightly over the course of each orbit, as the distance to the star increases and decreases by a small amount during each 18-hour circuit. This variation in tidal stress, though small, can pump energy into the planet's interior over billions of orbits, contributing to the geological activity and internal heat that distinguish this world from a cold, dead rock. The planet is alive with energy, both from above and from within. The surface of 55 Cancri, at least on the dayside hemisphere, is almost certainly a realm of molten rock, a global ocean of lava that flows and churns under the relentless radiation of the nearby star. Temperatures exceeding 2,000 degrees Celsius are sufficient to melt virtually any rock-forming mineral, leaving no solid ground for the imagination to stand upon. This lava ocean has existed for billions of years, maintained by the continuous input of stellar energy that keeps the surface far above the melting points of silicate or carbon minerals. The heat has nowhere to go except back into space as thermal radiation, a balance that keeps the surface at its current extreme temperature. Observations of 55 Cancri in infrared wavelengths have revealed that the day side is intensely hot, glowing with thermal emission that our telescopes can detect from 41 light-years away. The planet is not just hot on paper. We can actually see the heat radiating from its molten surface across the vast gulf of interstellar space. The exact temperature varies somewhat across the day side, with the hottest point directly beneath the star and cooler temperatures toward the terminator, where stellar radiation arrives at oblique angles. This temperature gradient would create flows of molten rock from hotter to cooler regions. The composition of this lava ocean depends on the underlying composition of the planet, which remains somewhat uncertain despite years of study. If the planet is silicate-rich like Earth, the lava would resemble the basaltic magmas that erupt from oceanic volcanoes on our world. If the planet is carbon-rich, as the diamond planet hypothesis suggests, the surface chemistry might be quite different, with carbon compounds participating in the molten mixture in ways we have never observed on Earth. The lava might contain dissolved carbon that would crystallize as graphite upon cooling. The boundary between the molten surface and any solid interior remains uncertain, depending on how deep the high temperatures penetrate and how the composition changes with depth. There might be a relatively thin lava layer floating on a solid or partially solid interior, or the melting might extend deep into the planet. Thermal models suggest the night side might be solid, or at least much cooler than the day side, potentially allowing solid carbon minerals to exist on the surface in the permanent shadow of the planet's dark hemisphere. The transition from molten day side to solid night side would create interesting geological features. Observations have detected significant variability in the thermal emission from 55 Cancri, with the brightness changing by tens of % over timescales of months to years. This variability suggests an active, dynamic surface rather than a static, unchanging lava ocean. One explanation for this variability is volcanic activity, eruptions that release additional heat and gases from the interior, temporarily brightening the planet before it returns to its baseline state. The planet might experience volcanic cycles on timescales accessible to human observation. Another explanation is changes in the reflectivity or composition of the surface, with different materials being exposed at different times as lava flows redistribute across the planetary surface. Fresh lava might have different properties than older, somewhat cooled material. The atmosphere might also play a role, with variable cloud cover or haze affecting how much of the surface we can see at any given time. An atmosphere containing vaporized rock or other exotic materials would interact with observations in complex ways. The comparison to Earth's volcanoes provides some intuition for the geological processes that might occur on 55 Cancri, though the scale and intensity differ enormously. On Earth, volcanoes erupt intermittently, local events that affect limited areas before cooling and solidifying. On 55 Cancri, the entire dayside hemisphere is essentially one continuous volcanic landscape, with no cool regions where rock has solidified and stabilized. The planet is a volcano without boundaries, an eruption that has lasted for billions of years. The lava ocean might have currents and waves, driven by temperature gradients and perhaps by tidal forces from the nearby star. These flows would operate under unfamiliar physics, with viscosities and densities determined by temperatures and compositions far outside our experience. We cannot see these flows directly from Earth, lacking the resolution to image the surface of a planet 41 light-years away. We can only infer their existence from the thermal variations we detect and from our understanding of how molten rock behaves under such conditions. The interface between the lava ocean and the atmosphere above represents a continuous exchange of material, with rock vaporizing into the atmosphere and atmospheric gases dissolving back into the melt. This exchange creates a feedback between surface and atmosphere that affects both. The atmosphere likely contains significant amounts of vaporized rock, silicon, and oxygen, and metals floating as gases that would instantly condense into solid minerals in any cooler environment. This rock vapor contributes to the atmospheric opacity and composition. When the planet passes behind its star and we lose sight of the dayside, observations have sometimes detected a decrease in certain spectral features, suggesting that these features arise from the hot dayside surface or its associated atmosphere. The planet hides its secrets when it hides its face. The molten surface of 55 Cancri represents one of the most extreme environments known on any planet, a world where the ground itself flows like water and the temperatures exceed anything we could survive or even briefly visit. Yet, this environment has persisted for billions of years. The detection of an atmosphere on 55 Cancri represented a significant milestone in exoplanet science, demonstrating that even small rocky worlds could retain gaseous envelopes despite extreme conditions that would seem hostile to atmospheric retention. This super-Earth, scorched by stellar radiation, nonetheless maintains an atmosphere. The atmosphere was detected through observations of the planet during secondary eclipse when it passes behind its star as seen from Earth. By measuring the light just before and during this eclipse, astronomers could determine how much light comes from the planet itself, revealing information about both temperature and atmospheric composition. The Spitzer Space Telescope, an infrared observatory that operated for many years before its retirement, provided some of the first atmospheric data on 55 Cancri. The planet's thermal emission varied with viewing geometry, suggesting an atmosphere that transports heat from the dayside toward the night side. More recently, the James Webb Space Telescope has observed this planet, bringing its unprecedented sensitivity and spectral resolution to bear on the question of atmospheric composition. Early results suggest an atmosphere unlike Earth's, dominated by heavier molecules rather than the nitrogen and oxygen we breathe. The composition of the atmosphere remains a subject of active research, with different observations and models suggesting different possibilities that have yet to be conclusively resolved. One possibility is an atmosphere rich in carbon dioxide and carbon monoxide, volcanic gases that might be continuously released from the molten surface. Another possibility is an atmosphere containing significant amounts of vaporized rock, silicon, and oxygen compounds that would be solid minerals under any normal conditions but exist as gases at the extreme temperatures of this world. Such an atmosphere would be truly exotic. Water vapor seems unlikely given the extreme temperatures and the probable chemistry of a carbon-rich world, though the question remains open until more definitive observations can be obtained. The James Webb Space Telescope may eventually resolve this question. The atmospheric pressure is unknown, as current observations cannot directly measure this property for exoplanets. The atmosphere might be thin, a tenuous envelope constantly being stripped away and replenished, or it might be substantial, a thick blanket that affects the surface conditions significantly. The survival of any atmosphere on a planet so close to its star requires explanation, as the intense stellar radiation and solar wind would tend to strip gases away over time. Several mechanisms might explain how 55 Cancri retains its atmospheric envelope despite these erosive forces. Continuous outgassing from the molten surface could replenish the atmosphere faster than it is lost to space, maintaining a dynamic equilibrium where loss and gain balance over time. Volcanic activity would provide the raw materials for this replenishment. The planet's gravity, substantially stronger than Earth's due to its greater mass, helps retain atmospheric gases that might otherwise escape. Heavier molecules are particularly well retained, which might explain why observations suggest a heavy molecule atmosphere rather than one dominated by light hydrogen. The magnetic field of the planet, if it possesses one, might also protect the atmosphere from erosion by the stellar wind, deflecting charged particles that would otherwise strip gases from the upper atmosphere. We do not know whether 55 Cancri has a magnetic field. The atmosphere of 55 Cancri almost certainly lacks any oxygen in its free form, as oxygen would quickly combine with other elements in the hot, reactive environment near the surface. Carbon monoxide, rather than oxygen, would be a more likely atmospheric component if carbon is abundant. The colors of the sky on this world, if the concept of sky even applies when the surface is molten and the atmosphere contains vaporized rock, would be unlike anything familiar from Earth experience. The scattering and absorption of light by exotic atmospheric constituents would create hues we cannot easily imagine. No clouds of water droplets would float through this atmosphere, but clouds of mineral vapor or condensed rock particles might form under the right conditions, perhaps in cooler regions near the terminator or on the night side. Such clouds would be made of substances we normally consider rocks. The thickness of the atmosphere affects how heat is transported around the planet, with thicker atmospheres able to move more energy from the hot day side to the cooler night side. Observations of the temperature contrast between hemispheres provide indirect evidence about atmospheric thickness. The atmospheric dynamics of a tidally locked planet differ fundamentally from those on Earth, where rotation creates the Coriolis force that shapes weather patterns and wind systems. On 55 Cancri, the dominant pattern would be flow from the hot day side toward the cooler night side. This day-to-night flow would rise on the hot hemisphere, where heating causes atmospheric gases to expand and become buoyant, then flow at high altitude toward the night hemisphere, before sinking and returning along the surface. The pattern resembles a global-scale convection cell. Winds at the surface might be relatively calm despite the extreme temperature differences, with most of the atmospheric motion occurring at higher altitudes where the pressure is lower. Alternatively, surface winds might be fierce, carrying heat and material around the planet. The interaction between atmospheric circulation and the possible lava ocean below adds another layer of complexity, with heat and material exchanging between liquid rock and gaseous atmosphere in ways that affect both domains. The boundary between surface and atmosphere might be gradual rather than sharp. Beneath the molten surface of 55 Cancri lies the hidden realm that gives this planet its famous nickname, an interior where carbon compressed by immense pressure may have crystallized into diamond throughout vast regions of the mantle. This diamond zone cannot be observed directly, but is inferred from the planet's overall properties. The mass of 55 Cancri, approximately 8 times the mass of Earth, has been determined through radial velocity measurements that detect the gravitational tug the planet exerts on its parent star. The radius, roughly twice Earth's, has been measured through transit observations that record how much starlight the planet blocks. Combining mass and radius yields the planet's average density, roughly 6 grams per cubic centimeter, somewhat higher than Earth's average density of 5.5 grams per cubic centimeter. This density must be explained by the materials composing the planet's interior and how they are arranged. Several different interior structures could explain the observed density, with carbon-rich and silicate-rich models both capable of matching the measurements within their uncertainties. The diamond planet hypothesis is consistent with the data, but not uniquely required by it. If the carbon-rich model is correct, the interior structure of 55 Cancri might be organized into distinct layers based on how carbon behaves under different pressure and temperature conditions. Near the surface, where pressures are lower, graphite would be the stable form of carbon. Graphite consists of carbon atoms arranged in flat sheets that slide easily past one another, giving the material its soft, lubricating properties that we exploit in pencils and industrial applications. A graphite layer near the surface might be tens or hundreds of kilometers thick. Below the graphite layer, at depths where pressure exceeds roughly 100,000 atmospheres, diamond becomes the stable form of carbon. The carbon atoms reorganize into a 3-dimensional crystal structure where each atom bonds to 4 neighbors, creating the hardest natural material known. This diamond layer might extend for thousands of kilometers, comprising the bulk of the planet's mantle and representing a quantity of diamond that dwarfs any terrestrial comparison. The pressures at the base of this layer would exceed millions of atmospheres. The core of 55 Cancri lies at the center of this layered structure, a region of extreme pressure and temperature where the planet's densest materials have settled over billions of years of differentiation. The composition of this core remains speculative. An iron or iron-nickel core similar to Earth's would be consistent with models of planetary formation, as iron is produced abundantly in stellar nucleosynthesis and tends to sink toward planetary centers due to its high density. The core might resemble Earth's in basic nature, if not in scale. Alternatively, the reducing conditions of a carbon-rich planet might favor the formation of iron carbide rather than pure iron, a compound where carbon atoms occupy spaces within the iron crystal structure. Iron carbide is harder and denser than pure iron. More exotic possibilities include cores containing unusual carbon phases that exist only under extreme pressure, forms of carbon that laboratory experiments have only recently begun to explore. The conditions at the center of a super-Earth exceed those available in most experimental setups. The pressure at the center of 55 Cancri reaches perhaps 10 to 20 million atmospheres, roughly 10 times the pressure at Earth's center. These extreme conditions could stabilize forms of matter that do not exist anywhere in our planet. Temperature increases with depth in planetary interiors, driven by the gravitational energy released during planetary formation and by radioactive decay of elements like uranium and thorium. The core temperature of 55 Cancri might exceed 10,000 degrees Celsius. At such temperatures, even diamond might begin to melt or transform into other phases, depending on the pressure. The carbon phase diagram at extreme conditions is not fully mapped, leaving uncertainty about the state of carbon at the planet's center. The internal heat of the planet flows outward over time, conducted through the various layers, and eventually radiated into space from the surface. This heat flow contributes to the geological activity and volcanic processes that maintain the molten surface. The diamonds in the interior of 55 Cancri, if they exist, formed not through the geological processes that create diamonds on Earth, but simply through the ambient conditions of a carbon-rich planet. On Earth, diamonds form in specific locations where carbon-bearing materials are subjected to high pressure. On a carbon planet, diamond would be the ordinary state of carbon throughout vast regions of the interior, not a rare gem, but a common rock-forming mineral as mundane as granite is on Earth. The preciousness we attach to diamond reflects its rarity in our oxygen-rich world. A hypothetical miner on 55 Cancri E would find diamond everywhere, as common as dirt, useful perhaps as a building material or industrial abrasive, but not as a store of value. The context that makes something precious is entirely local. This shift in perspective is one of the profound lessons of planetary science, the recognition that the conditions on Earth are not universal, but merely one possibility among many. What is rare here might be common elsewhere, and what we value might be worthless in a different context. The diamond planet is the innermost of 5 known worlds, orbiting 55 Cancri, a planetary system that ranks among the most extensively studied beyond our own solar system. Each planet occupies its own orbital zone, tracing paths that have remained stable for billions of years. 55 Cancri b, the second planet outward from the star, is a gas giant roughly 8 times the mass of Jupiter, orbiting at about 90.1. This massive world was among the first exoplanets ever discovered, detected in 1996 through radial velocity measurements. The discovery of 55 Cancri b predated the discovery of the diamond planet by more than a decade, establishing this star as a planet host before the inner super-Earth was found. The system has been monitored continuously since that first discovery. 55 Cancri c orbits beyond the first gas giant at about 0.24 astronomical units, with a mass roughly 1/6 that of Jupiter, placing it in the Neptune mass category. This intermediate world completes an orbit in about 44 days. 55 Cancri f occupies an orbit at about 0.78 astronomical units, roughly 3/4 the distance from Earth to the Sun, with a mass about half that of Saturn. This world orbits in roughly 260 days, approaching an Earth-like year length. The outermost known planet, 55 Cancri, is a gas giant roughly 4 times the mass of Jupiter, orbiting at about 5.7 astronomical units. This places it beyond the habitable zone in a region similar to Jupiter's position in our own solar system. This outermost planet takes roughly 14 Earth years to complete one orbit, a long period that required many years of observation to confirm. The patient accumulation of radial velocity data eventually revealed the full extent of this planetary system. The architecture of the 55 Cancri system differs markedly from our own solar system, with a super-Earth scorching close to the star and gas giants, distributed through the middle and outer regions. The arrangement challenges simple models of planetary formation. The presence of 5 planets in this system demonstrates that complex planetary systems can form and remain stable around stars other than the Sun. A finding that was not guaranteed before exoplanet surveys began revealing the diversity of planetary architectures throughout the galaxy. The gaps between the planets in the 55 Cancri system might contain additional worlds too small or too faint to have been detected by current methods, lurking unobserved in regions where their gravitational effects remain too subtle to measure. Future observations might reveal additional family members. The gravitational interactions among the 5 known planets create subtle perturbations in their orbits, effects that careful analysis can use to refine estimates of planetary masses and orbital parameters. The planets do not move independently but influence each other continuously. The long-term stability of this 5-planet system over billions of years required specific conditions during formation. Orbital arrangements that avoided the resonances and close encounters that could have ejected planets or sent them crashing into the star or each other. The formation of this system likely began in a disk of gas and dust surrounding the young star 55 Cancri A, a rotating cloud that gradually condensed into planets over millions of years. The innermost regions formed hottest and fastest, while the outer regions took longer to assemble. The diamond planet, if it is indeed carbon-rich, may have formed from materials that condensed in a region of the disk where carbon compounds were stable, then migrated inward to its current extreme orbit through interactions with the remaining disk gas. Migration is common in planetary system evolution. The gas giants formed farther out, where conditions allowed them to accumulate thick hydrogen and helium envelopes, growing massive through a runaway process that captured gas from the surrounding disk before it dissipated. Their current positions may or may not reflect where they originally formed. The history of this system is written in the orbital properties of its planets, a record that astronomers are still learning to read. Each measurement of mass, radius, or orbital element provides another clue to the events that shaped this family of worlds. The 55 Cancri system provides context for the diamond planet, reminding us that this exotic world exists not in isolation, but as part of a complex planetary family. The innermost world is extreme, but the system as a whole displays a variety of planetary types. The gas giants in the outer system are more similar to Jupiter and Saturn than the inner super-Earth is to anything in our solar system. The system contains both familiar and exotic elements, a mixture of the expected and the surprising. This combination is typical of exoplanetary systems in general, which often contain planets resembling those we know alongside planets unlike anything orbiting our Sun. The universe explores many possibilities simultaneously. 55 Cancri stands out within its system, and within the broader exoplanet catalogue because of its combination of properties: close orbit, super-Earth mass, high temperature, possible carbon composition. Each property alone is known in other worlds, but the combination is special. The distance separating Earth from 55 Cancri A spans 41 light-years, a measure of space that places this diamond world among the closer exoplanets to our solar system, while still representing a gulf that no current technology could cross within any human lifetime. A light year is the distance light travels in 1 year, roughly 9.5 trillion kilometers of empty space that light crosses at 300,000 kilometers per second. 41 years of travel at this ultimate speed separates us from the diamond planet. The light arriving at Earth tonight from 55 Cancri left the star in the early 1980s, beginning its journey while personal computers were novelties and the internet was a research project known only to specialists. That light has traveled while 4 decades of human history unfolded. Whatever is happening on 55 Cancri right now, at this precise moment, will not be known to Earth observers until the 2060s, when the light from the current moment finally completes its crossing. We observe the past and must wait for the present. This delay between event and observation defines all astronomy beyond the immediate solar system, where the speed of light creates an insurmountable lag between reality and our perception of it. We never see the universe as it currently is, only as it was when the light began traveling. For 55 Cancri, 41 years is a short delay by cosmic standards, barely noticeable compared to the billions of years the planet has existed. The world has not changed significantly between the light's departure and our observation of its arrival. The volcanic surface still flows, the atmosphere still churns, the diamond interior still exists under crushing pressure. All of these conditions persist across the decades of light travel time with negligible change. The universe is patient on these timescales. The relative proximity of 55 Cancri has made it an intensively studied system, close enough that our best instruments can extract detailed information about its planets. More distant systems remain more mysterious, their light fainter, and their properties harder to measure. Traveling to 55 Cancri with current technology would require timescales that dwarf human civilization. Journeys of hundreds of thousands or millions of years at the speeds our fastest spacecraft have achieved. The Voyager probes, now leaving the solar system, travel at roughly 17 kilometers per second. At Voyager's speed, the crossing to 55 Cancri would take roughly 700,000 years, a duration that exceeds the entire existence of anatomically modern humans by many times over. No mission using current propulsion could deliver results within any relevant time frame. Theoretical technologies that might someday achieve higher speeds, nuclear pulse propulsion, solar sails, antimatter engines, could shorten the journey but still leave it measured in centuries or millennia rather than human lifetimes. The stars remain effectively unreachable. This distance ensures that our knowledge of 55 Cancri will come entirely from light, from photons that cross the void, to bring information about a world we can study but never visit. We are observers only, limited to what light can tell us. The constellation Cancer, where 55 Cancri appears in Earth's sky, is visible in the northern hemisphere during winter and spring months. A faint constellation located between the brighter patterns of Gemini and Leo. Finding it requires patience and reasonably dark skies. Within this constellation, 55 Cancri shines at the edge of naked eye visibility, a point of light that carries little obvious distinction from thousands of other dim stars scattered across the night sky. Only knowledge elevates it to significance. Yet that point of light represents photons from a star that hosts one of the most exotic planets ever discovered. A world that might contain more diamond than exists on all the terrestrial planets of our solar system combined. The unremarkable appearance belies the remarkable reality. Looking toward 55 Cancri on a clear night creates a direct physical connection to the diamond planet, a line of sight along which photons have traveled for 41 years to enter the observer's eye. The connection is real, even if the distance makes it seem abstract. The impossibility of visiting 55 Cancri does not diminish the value of knowing it exists, of understanding its properties, of imagining what conditions prevail on its molten surface and in its crystalline interior. Knowledge has value independent of practical application. Humanity has always sought to understand the cosmos. to map the stars and comprehend the worlds that orbit them, driven by curiosity that requires no justification beyond itself. The diamond planet rewards this curiosity with wonder. The distance ensures that wonder is all we can directly experience. The vicarious thrill of knowing that such a place exists somewhere in the galaxy, real and physical, and subject to the same laws of nature that govern our own world. Imagination bridges what rockets cannot. Future generations may develop technologies that shrink interstellar distances, methods of travel or communication that we cannot currently envision. Until then, 55 Cancri A remains a destination for telescopes and imagination rather than spacecraft. The characterization of 55 Cancri A as a diamond planet rests on a chain of inference that, while plausible, contains significant uncertainties that honest scientific discussion must acknowledge. The planet might be diamond-rich, but it might also be something quite different. The original diamond planet hypothesis emerged from studies suggesting that the star 55 Cancri A has an elevated carbon-to-oxygen ratio, higher than the Sun's, which would favor the formation of carbon-rich planets from the surrounding disk material. This stellar composition set the stage. Subsequent studies of the star's composition have yielded mixed results, with different analyses finding different carbon-to-oxygen ratios depending on the spectral lines examined and the methods used for analysis. The stellar evidence for carbon enrichment is suggestive but not conclusive. Even if the star is carbon-rich, this does not guarantee that its planets inherited this composition, as the planet-forming disk might have had different abundances in different regions. The connection between stellar and planetary composition remains imperfectly understood. The measured density of 55 Cancri A is consistent with a carbon-rich interior, but does not uniquely require it. Alternative compositions involving silicate rock and iron could also match the observed mass and radius within the measurement uncertainties that currently exist. Some models suggest the planet might be more Earth-like in composition than the diamond planet hypothesis implies. With a silicate mantle and iron core covered by the molten lava that observations have detected, the lava ocean is real. The diamond interior is inferred. The variability observed in the planet's thermal emission complicates interpretation, suggesting a dynamic surface whose properties change over time. This variability might reflect volcanic activity, atmospheric changes, or processes we have not yet considered. Recent observations with the James Webb Space Telescope have provided new data about the planet's atmosphere and surface, data that scientists are still analyzing and interpreting. The picture continues to evolve as new information arrives. The uncertainty about 55 Cancri A's composition illustrates a general feature of exoplanet science, where planets are characterized primarily through remote observation and theoretical modeling rather than direct sampling. We cannot scoop up a handful of the planet to analyze. This limitation means that conclusions about exoplanet interiors are always provisional, subject to revision as new data become available or as theoretical models improve. What seems likely today might be contradicted or refined by tomorrow's observations. The diamond planet hypothesis remains viable, supported by enough evidence to make it worth considering seriously, but it should be held with appropriate humility about what we actually know versus what we infer or assume. This uncertainty does not diminish the scientific interest in 55 Cancri A, which remains a fascinating world, regardless of whether its interior is diamond-rich or composed of more familiar materials. The extreme surface conditions and orbital parameters are established beyond reasonable doubt. The process of scientific investigation involves exactly this kind of ongoing refinement, hypotheses proposed and tested, Conclusions drawn and reconsidered as evidence accumulates over years and decades. The diamond planet hypothesis is part of this process. If future observations demonstrate that 55 Cancri is silicate-rich rather than carbon-rich, this would not represent a failure of science, but rather its normal operation. Hypotheses are meant to be tested, and some are meant to be discarded. The value of the diamond planet idea lies not just in whether it turns out to be correct, but in how it has shaped investigation, prompting observations and analyses that deepen our understanding regardless of the ultimate conclusion. Science progresses through exactly such creative proposals and careful testing. Imagination constrained by evidence, speculation refined by observation. 55 Cancri has been a productive subject for this process. What we can say with confidence is that 55 Cancri E is a super-Earth, roughly twice Earth's diameter and 8 times its mass, orbiting extremely close to its parent star in a period of just 18 hours. These properties are well established. We can say that the dayside surface reaches temperatures exceeding 2,000 degrees Celsius, hot enough to melt rock, and likely maintaining a global lava ocean on the hemisphere facing the star. Thermal observations confirm this extreme heating. We can say the planet has an atmosphere of some kind, detected through observations of its thermal emission and possibly containing exotic gases released by volcanic activity. The atmosphere has been detected even if its exact composition remains uncertain. What we cannot yet say with certainty is whether the interior contains diamond on a planetary scale, whether the carbon-to-oxygen ratio favored carbon planet formation, or whether this world's depths glitter with crystallized carbon. These questions remain open. The diamond planet continues its 18-hour orbit as these words settle into the quiet of the evening, racing around its ancient star, whether anyone observes its passage or not. The world has circled its sun countless billions of times already, each orbit identical to the last, within any precision we could measure. The molten surface flows and churns under the relentless radiation, lava oceans that have existed for longer than life has walked on Earth. Longer than the continents we know have held their current shapes. The heat pours down continuously from a star that will not significantly change for billions of years yet. Beneath that flowing surface, in regions we can infer but not observe, the interior of 55 Cancri extends downward into realms of increasing pressure and mystery. Whether diamond forms the bulk of those depths, or whether more familiar silicates prevail, the planet keeps its secrets locked away from distant observation. The uncertainty does not diminish the wonder of knowing such a world exists, real and physical, and subject to the same natural laws that govern the stones beneath our feet. A super-Earth orbiting in 18 hours, heated to thousands of degrees, possibly containing diamond on a planetary scale. The facts themselves carry weight. The star 55 Cancri A has burned steadily for 10 billion years, twice the age of our Sun, providing warmth to whatever worlds formed around it across timescales that humble human comprehension. The star will continue burning for billions of years more before beginning its final evolution. When that evolution finally comes, the star will swell into a red giant, its outer layers expanding to engulf or destroy the innermost planet that we have contemplated tonight. The diamonds, if they exist, will vaporize back into carbon vapor, the geological record erased. But that destruction lies far in the future, so far that the span of human history would need to repeat millions of times before its arrival. For now, the planet orbits, the surface flows, the interior exists in whatever state it has occupied since the system's youth. The light from 55 Cancri streams through space at 300,000 kilometers per second, carrying information about temperatures and compositions toward any world that happens to lie in its path. Some of that light is currently traveling toward Earth. The night sky contains thousands of visible stars and billions more beyond the reach of unaided vision, each potentially hosting its own family of planets. 55 Cancri is one among these countless points of light, distinguished by what we have learned about the worlds orbiting it. The diamond planet, if that is what it truly is, represents one possible outcome of planetary formation, one path through the vast space of possibilities that the universe explores as stars and planets form throughout the galaxy. Other paths produce other kinds of worlds. Some planets are gas giants, massive spheres of hydrogen and helium with no solid surface at all. Some are icy worlds in the outer reaches of their systems, frozen seas beneath frozen skies. Some are rocky worlds like Earth, with silicate crusts and iron cores, and some perhaps are carbon worlds, built from graphite and diamond and silicon carbide, worlds where carbon rather than oxygen dominates the geology. 55 Cancri may be our best glimpse of this exotic category. The image of a diamond world can accompany you now as wakefulness begins to fade. A planet of fire and crystal spinning through its tiny orbit around a star, 41 light-years distant. The surface glows molten orange. The interior perhaps glitters with compressed carbon. The star blazes overhead without setting. The extreme heat and pressure of this world exist in the same universe as the gentle night that surrounds you now, governed by the same physics, made of the same fundamental particles arranged in radically different configurations. The connection is real, however distant. The photons from 55 Cancri that will arrive at Earth in 41 years are currently partway through their journey, crossing the void in straight lines at the speed of light. Nothing will hurry them, nothing will slow them. They simply travel as light always does. The planet races through another orbit as you rest, completing another 18-hour year while hours pass on Earth. The scale difference is immense, the planet sprinting where Earth ambles, the star looming where our sun appears modest. The constellation Cancer holds its position in the sky, turning slowly as Earth rotates, carrying its dim stars, including 55 Cancri, across the celestial sphere. By morning, the constellation will have moved, though the stars within it maintain their fixed relationships. The universe continues its operations on scales of time and space that dwarf individual human concerns. Stars burning, planets orbiting, light traveling between them in journeys that take years or centuries or millennia. Nothing waits for human attention. This independence is not cold but restful, a reminder that the cosmos does not depend on our awareness to proceed, that wonders exist whether or not we contemplate them. The diamond planet neither knows nor cares that minds on a distant world have spent an hour considering its nature. The knowledge flows in one direction only, from that distant world to our patient observation. And even then, the knowledge is incomplete, uncertain, subject to revision. We know what we know and hold the rest lightly. The questions that remain unanswered about 55 Cancri can rest now. Open questions that do not demand resolution tonight or any night. Science will continue its patient investigation, and understanding will grow incrementally over years and decades. What matters tonight is the wonder, the expansion of imagination that comes from considering a world so different from our own. A planet where the ground might be diamond and the surface flows with molten rock. The facts have served their purpose. The diamond planet exists whether or not we solve every mystery about its composition. whether or not the carbon-rich hypothesis survives future testing. The world is real, orbiting right now as these words fade into the quiet. Let the image settle, the fire and the crystal, the ancient star and the racing planet. The 41 light-years of void that carry information but permit no passage. The distance is absolute for now, perhaps forever, and that is acceptable. The diamond world continues its orbit through the cosmic dark, a jewel of uncertain composition, spinning around a star older than our sun, keeping its secrets beneath a molten surface that glows with heat borrowed from stellar fires. The planet does not sleep, but you may. Good night from the drowsy astronaut. Sleep well, and we'll explore the cosmos together again soon.